Hello, dear students. Today we are going to discuss the IR spectroscopy. This is a typical IR spectrophotometer, the diagram of an IR spectrophotometer. This is the IR radiation source, normally a tungsten light. When it passes here through a slit, it is then divided into two. One goes to in one direction and the other in the other direction. Then it is reflected by mirrors here and then passes through a slit. So we have monochromatic light here. Then one passes through reference and the other through the sample. It is again reflected by mirrors and then it passes through the splitter and then through detector, and the detector detect the radiations, and then we get a spectrum from the spectrometer or spectrograph. As we have previously discussed that the IR region is from zero point 0.8 micrometer or 800 nanometer to 1 millimeter, 1 nanometer, 1 millimeter or 1000 micrometer. It is then subdivided into near IR, that is 0.8 to 2 micrometer, middle IR, that is 2 to 15 micrometer, and far IR, which is 15 to 1000 micrometer. The middle IR is the region of interest of the chemist because nearly all compounds give spectrum in this region. Most of the analytical applications are confined to the middle IR region because absorptions of organic molecules are high in this region. What happens in the IR, or what the IR radiation causes in the molecule, and what are the necessary conditions for a molecule to absorb the IR radiation. A molecule can only absorb IR radiation when its absorption causes a change in its electric dipole. A molecule is said to have an electric dipole when there is a slight positive and slight negative charge on its component of atoms. Those molecules which have a slight charge on the molecules, that is, one has a slight positive charge and the other has a slight negative charge, are called dipolar molecules. And only the dipolar molecule can absorb the IR radiation because this radiation causes a change in its dipolar moment. There are two types of vibrations in the molecular vibrations. One is stretching vibrations, the other is bending vibrations. The stretching vibrations are oscillating along the line of bond, change in bond length, and they occur at higher energy, 4000 to 1250 per centimeter. The stretching vibrations are of two types. One is the symmetrical stretching and the other is the asymmetrical stretching. This is change in interatomic distance along bond axis. These are the stretching vibrations. This is the symmetric stretching, that both the groups relax and expand at the same time. While in the asymmetric vibrations, one is expanded and the other is compressed. This is the symmetrical stretching, this is the asymmetric stretching, and this is the twisting. The symmetrical stretching. The two bonds increase or decrease in length simultaneously, as like we have seen in the previous diagrams. The two bonds expand or increase or decrease simultaneously at the same time. Asymmetrical stretching. In this, one bond length is increased and the other is decreased. At one time, one bond length will increase and the other bond length will decrease. And at the other time, this bond length will decrease and this bond length will increase, as we have seen in the previous slides. Bending vibrations. This is the second type of vibrations. One was stretching and the other is bending. Vibration or oscillation not along the line of bond. These vibrations or oscillation are not in the line of bonds. These are also called deformations. In this, bond angle is altered. In the stretching vibration, the bond length was changing. But in the bending vibrations, not the length, the angle is changed. They are comparatively low energy vibrations, and these occur from 1400 to 666 per centimeter. These are of two types. The bending vibrations are also of two types. One is in-plane bending, that is scissoring or rocking, and the other is out-of-plane bending, that is wagging and twisting. The twisting we have seen in the previous slide. We will see the others. Bending, change in angle between two bonds. There are four types of bending. Rocking, this is in plane. The change in angle in plane, this is rocking. Then the bending vibration, these are also in plane. These are scissoring. This is out of plane. The two goes near or far from each other, and these are wagging. And this is one is also out of plane. One is near, one is far. One is near, one is far. This is out of plane twisting. So the bending vibrations are rocking, scissoring, wagging, and twisting. The rocking and scissoring are in plane vibrations, while the wagging and twisting are out of plane vibrations. And as we have previously discussed, that in the stretching vibration there is a change in the bond length, but in the bending vibrations there is a change in the bond angle. These are scissoring, rocking, and wagging. In plane bending, scissoring. This is an in plane bending. The two atoms approach each other, bond angles are decreased. They approach the two atoms approach each other simultaneously at the same time. and bond angles are decreased. Rocking. The bond movements takes place in the same direction. They will be moving in the same direction at the same time, either left or right, in the same direction. So this type of movements, this create rocking or rocking molecule motions. Then is come the out of plane bending. The previous one, the rocking and scissoring, these were in plane bending, while these one, the wagging and twisting, these are out of plane bending. In wagging, the two atoms move to one side of the plane, they move up and down the plane. In wagging, the two here atoms move in one side of the plane. Either will be up or either will be down the plane. While in twisting, one atom moves above the plane and another atom moves below the plane. In the twisting, these one atom will at one time move above the plane and the other will move below the plane. And at the other time, this one will move above the plane and this one will move below the plane. So the two atoms will move above and below the plane, but not at the same time. Vibrational coupling. In addition to vibrations mentioned above, interaction between vibration can occur. This is called coupling. If the vibration bonds are joined to a single central atom, vibrational coupling is influenced by a number of factors. Strong coupling of stretching vibration occur when there is common atom between the two vibrating bonds. Coupling of bending vibrations occur when there is a common bond between two vibrating groups. Coupling between a stretching vibration and a bending vibration occur if the stretching bond is one side of an angle varied by bending vibration. Coupling is greatest when the coupled groups have approximately equal energies. No coupling is seen between groups separated by two more bonds. Like we have discussed that there are some fundamental vibrations. These vibrations are in plane and out of plane. The in plane are stretching vibration. The stretching are then symmetrical and asymmetrical. Then are the bending vibrations. The bending are rocking, scissoring, twisting and wagging. And every type of vibration, these has their particular energy. But sometimes what happens that the two vibrations couple with each other. That may be two bending vibrations, or that may be a bending and a stretching vibration. But the coupling, one necessary condition for the coupling is that these atoms must have a common atom to which they are attached. Like the coupling of bending vibration occur when there is a common bond between the vibrating groups. The coupling between a stretching vibration and a bending vibration occur if the stretching bond is on one side of an angle varied by bending vibration. And the coupling is greatest when the coupled groups have approximately equal energy. If the groups are separated by two or more bonds, no coupling will occur. The coupling frequency will be different from the fundamental frequency and will be an approximate sum of the two coupled frequencies. General uses of the IR: identification of all organic and many types of inorganic compounds, determination of functional groups in organic material, determination of molecular composition of surfaces, identification of chromatographic effluents, quantitative determination of compound in mixture. It's a non-destructive method because the IR or infrared radiations are quite weak and it cannot change the bond length or it cannot destroy the bonds. Determination of molecular conformation like structural isomer and stereochemistry, geometrical isomers. The determination of molecular orientation, polymers and solutions. Applications. Some common applications of the IR spectroscopy. Identifications of compounds by matching spectrum of unknown compounds with reference spectrum. Identification of functional groups in unknown substances. Identification of reaction compounds and kinetics studies of the reactions. Identification of molecular orientation in polymer films. Detection of molecular impurities or additives present in amounts of 1% and in some cases low as 0.01%. Identification of polymers, plastics and resins. Analysis of formulations such as insecticide and copolymers. There are some limitations of the IR spectroscopy or this method for the identification. Minimal elemental information is given for most sample. IR doesn't give the elemental information that how much of certain elements are present in a compound or in a molecule. Background solvent or solid matrix must be relatively transparent in the spectral region of IR. The solvent or the matrix which is used, but nowadays there are the IR instruments which use directly the sample and without any matrix. Molecule must be active in the IR region, like it must have a dipole moment. When exposed to IR radiation, a minimum of one vibration motion must alter the net dipole moment of the molecule in order for absorption to be observed. As we have already discussed that only the dipolar compounds can absorb the IR spectroscopy or can absorb the IR radiations. Accuracy. In analysis of mixture under favorable condition, accuracy is greater than 1%. In routine analysis, it is plus minus 5%. Sensitivity and detection limits. In routine operation, it is 2%. Under most favorable condition and special techniques, it is 0.01%. So it is quite sensitive instrument, but in routine it is nearly 2% sensitive. It has nearly 2% of sensitivity. Thank you so nice of you for your patience. Thank you.